Okay, let's go ahead and get started. Just a couple of reminders as usual. Lab 8, current lab. No, some of you have been emailing me, so you're starting it. Bunch of data sets. Use Input Analyzer. You kind of learn how to use Input Analyzer to do the fitting. For generation of histograms, you'll notice in the Input Analyzer, histogram is really just meant to be a prototyping tool to help you kind of see roughly what the shapes are and if they kind of make sense. Then if you want to like put a histogram in a report, you would never use the Input Analyzer histograms. You notice they don't have any axes, titles. They're just kind of ugly. And so when I talk, I think in the Lab 8 video about generating kind of more production quality or report quality histograms, I mean, you can use Excel or something like that to generate those histograms. And that way you have easy control in Excel over things like bin size and bin width and all of that as well. And plus you can adjust the titles and the axes and all of those. And so the Input Analyzer's histogram tool is really just meant there to kind of help you spot check as you're fitting models. It's not meant to be something that you should like take a screen cap of and put into a report or something like that. So it's a little ugly, but it's not meant to be a reporting tool. Yeah.
So I tried to export the data file to CSV.
Mm-hmm.
So I analyze it, but it's asking for the CSV file.
Well, so there's questions. So in order to, so when you export the data to Input Analyzer, you can save it as a .csv file. And I think if you do file open on Input Analyzer, you can select like all files and then it'll show you those. Otherwise, you can rename that CSV file a DST file and it should be able to open it. Well, then email me and I can help you with that. Maybe I might have to run, but so yeah, we'll see if we have time after class and you can come up and but in general, it's basically just looking for flat files that don't actually have to be CSVs. They're just a column of numbers. And so as long as there is a flat column of numbers, then you might have problems with line endings or whatever, but I can help you debug that. And if you do have any troubles getting these in the Input Analyzer, email me or email Shin, and we can help you with sort of the common kind of pitfalls there. But we gave you a variety of different types of data, continuous and discrete, meant to kind of help prepare you for the type of data you'll see when collecting data for your final project. And so the goal of next week's lab is to help you, or next week's lab time is to give you time to work on your input modeling report, where the main, so detailed data is on Canvas on the input modeling report, but the function of the input modeling report is in 1 to 2 pages, so not very long. Tell me the system that you're interested in, the relevant problems that motivate why you would study that system, and then what you think are the input models or the inputs to those systems, maybe the relevant entities, the relevant resources, and maybe the outputs that you would think of taking there. And then show me that you have access to the system by going out and sampling from some of those inputs and maybe doing a crude input model. And so it's not meant, you're not meant to gather all of the data that you possibly need, but it's meant to just demonstrate that, we've gone out, we've taken data on this particular input, we have these other inputs we need to take data on, but we have the ability, we have access to the system, we can take the data, and we have practiced our ability to fit real models to real data. And so that's kind of the goal here, is just to make sure that at this point you have some momentum built up, because really after the input modeling report, we kind of let you go. And so there'll be 2 labs that you're doing the lab period and then the open lab here. But we want to make sure that you're not doing this part, close to the very end of the semester. And so once you're here, you've at least picked the system and started working with the system. And that's the reason why we have you do this here. And then we kind of leave you alone after that. Okay, so any questions about this schedule? And then online, anything in the chat? Okay, all right. So I've kind of covered this. The deliverable that's due even sooner than the input modeling report is this names of team members. Almost, more than half the class has submitted this. So if you're still having trouble finding a team member, there is that Google spreadsheet. If you've gone into the Google spreadsheet and added a line, you should maybe go back and then see who else has added it, and then feel free to contact each other and link up. If you've got a 3-person group, it's probably going to be fine. I think all of the groups I've had so far are 4-person groups. I probably am going to need at least one 3-person group, just based on, I think there's like, I don't know, I think there's 51 students in the class. And so if there's all 4-person groups, then we're going to have at least one, 3-person left over. So, if you can't quite find the 4th person, it's okay to submit that 3-person group, because we'll probably can tolerate a couple of those. And all all members of the group need to submit that. So even if somebody else in your group has already submitted theirs, make sure you submit it as well. That way I can confirm that everyone agrees on who's in their group. After that, then I'll put you into groups, and your other things like the input modeling report, the final project report, the final presentation, those will all be group uploads. Only one person will have to upload that. And then the next deliverable soon after that is this input modeling report. The details on the structure of that is on Canvas. I've already kind of chatted a little bit about that. And so there'll be no formal lab next week. Next week's lab time is meant to provide you formal time for you to maybe go out and take some data or something like that. So we're not burdening you with an additional lab next week while you're working on that. So that the lab report for next week is really the input modeling report. Okay, other assignments. We've got ICA H is coming out, and then there's a couple other ICAs. So there's only 3 more ICAs before the final review ICA. Homework G3 has been posted, just 2 questions. The first one is a chi-squared test, very similar to probably what you've seen in other classes, where you're just going to be evaluating a Poisson fit, both with an estimated parameter and a given parameter. So those 2 things will change how the chi-squared's done in ways we'll talk about today. And then there is an output validation problem. So you'll be doing a power analysis, or actually a paired t-test and a power analysis for question 2. And we will cover that by lecture H. And so whereas most homework assignments, I give you about 1 week, I've given you about 2 weeks of this, because that way you have some time to see me cover it in lecture H. But if you want to work ahead, the power analysis stuff is also, there's material that's linked right out of the homework assignment on Canvas or under that module there, if you want to look ahead on how to do that power analysis, if you've not done a power analysis in your other courses yet. Okay. All right, so any questions about the admin stuff here? Okay. All right, great. Okay, so where we were last time, just trying to motivate how important input modeling is. You start out with a structure of a system like this simple single server queue. And so in this particular case, we might depict this abstractly with symbols like these, which you might use more of this in like 470, and we would abbreviate our input models with something like Kindle's notation, something I'm not going to test you on in this class, but when you take classes like 470, then you'll get more familiar with Kindle's notation in sort of compactly summarizing the input models that occur at different nodes in a queuing network. And so this particular system has got an interarrival process, and it has a service process. And that interarrival process, there's in this Kindle's notation, the first M is short for it being Markovian or memoryless, in other words, an exponential. The second M means that the service times are also exponential. And then the 1 means there's 1 server. And so that's a nice compact way to say all of these input models. And so you could imagine putting very different distributions in these 2 different boxes, and you would get very different outputs from this queuing node. So it's really important to get those input models right. In fact, you can, there's a whole Wikipedia page on Kindle's notation where they list all of the kind of different options for the kind of Lego bricks that you would plug in here. So the Lego brick that goes in the interarrival process, all the different codes, the Lego brick that goes to the service distribution, all the different codes. And so you could imagine you pick a letter from this one, you pick a letter from this one, you pick a number, and the same exact structure in Arena will have very different output statistics. And so this is just driving home that the choice of input model is super important. And the big thing that might differentiate a bank from a McDonald's might not be how the structure of the store is set up, but might be how people arrived to the bank versus how they arrived at McDonald's, or how quickly, what the distribution of service times looks like at the McDonald's versus the bank or something like that. So really the shape of these distributions is just as important as the structure of the system, which is what we're kind of driving home here. So this whole unit G, is about how do we choose good input models for these boxes. And so where we left off last time, so this is going back to a couple of lecture G2 slides that I wasn't able to get here, is that we've got this general process of collecting data, looking at data, identifying a probability distribution, and then what we'll do later today here is choosing parameters and testing goodness of fit. But in order to identify this probability distribution, last time I talked about all of these different tools for looking at the data, like histograms and so on. And where I left off here are these probability plots. And so once you've made a guess of a family, so you look at the data and the histogram looks kind of bell-shaped, and you might say, okay, this I think is normally distributed. Well, how do I get a better, you can just look at it and kind of looks bell-shaped, but then if you look at a lot of the other distributions, there are a lot of other distributions that kind of can look bell-shaped too. So how do I get something a little bit closer to a quantitative assessment of whether I picked a good family of distributions before I manage to parameterize them? And probability plots, which if you've talked about fat pencil tests in any of your other courses, then that's where these come from. This is a way to very quickly plot your data in a more informative way against one of these hypothetical distributions. And there are two that we worry about: the so-called QQ plot and the PP plot, which are very similar, but you're just plotting the data in kind of a slightly different direction in each one of these. And so for both of these plots, your step is to sort your data in just like you would with a KS test. In fact, these are kind of related to a KS test. And then once they're sorted, then you can plot sort of which one, it's whether you're plotting the data or it's quantile. And so in the QQ plot, you're effectively plotting the sample CDF against a hypothetical CDF. So the Q here stands for quantile, which is another name for inverse CDF. And so, I'm plotting the quantile versus the quantile. So I said sample CDF. I guess technically I meant the sample inverse CDF versus the empirical inverse CDF. And so whereas the PP plot is probability, you're not comparing quantiles, you're comparing probabilities. So the axes of a QQ plot are going to be the range of your data. The axes of a probability plot are going to be 0 to 1, because you're plotting probability versus probability. And so let's see this more concretely here. So if I focus on just the QQ plot, then what I do is I sort all of my data in ascending order, and then I plot each data point. Now remember, in a sample CDF, I would plot the data point against its rank. So I'd be like the data point against I divided by N, where I would be its position in the rank and N would be the number of data points. But I'm not going to do that exactly. I'm going to take the inverse CDF of my hypothetical distribution, and then I'm going to then use that to transform the rank into, this is kind of like an inverse transform method. It's almost like I'm drawing a random number where my random number is the rank. And so I am sort of finding this so-called quantile. So I'm saying that if this data point occurs at the median, that would mean if it occurs at 50% of the data, 50% are below it, 50% are above it, what point occurs at 50% of my hypothetical distribution? I'm going to plot those two things together. That's what the QQ plot does. And then I look for a linear relationship. So if, for example, I've got data that I've drawn from a normal distribution with mean of 5 and standard deviation of 9. And so I imagine I didn't know where I drew it from. I just got data. I have no idea what it is. But in this case, I'm telling you, ground truth, I just happen to know that I drew them from a normal distribution with these parameters, 5, 9. And I look at that as a histogram, and it looks kind of bell-shaped. And so now I want to say, maybe this is normally distributed. How good is my guess at the normal family? So I'm going to do a QQ plot against it in the standard normal, which is just centered at 0 with a variance or a standard deviation of 1. And so when I do that, I can see that on this axis, I've got kind of the range of my samples. So notice they're like all over the place because this is like centered at 5. So the mean is around 5, and also the mode, I guess. And then it goes to kind of negative infinity and positive infinity. And then my hypothetical, it's centered at 0. And so then it goes to the positive infinity, negative infinity from there. And so I've kind of lined these up by their quantiles here. And I see that they fall right on a line here. So even though the data that the distribution I drew it from had different parameters, because it's shaped the same, it still fell on a line with a hypothetical that was a standard normal. So this is not a standard normal, but it happens to be normal. And so it falls on the line here. So even before I know what the right parameters are, this tells me that, yeah, these data are looking pretty normal. So I have a student who is writing a paper right now on a particular inference that he's making on these little ants that carry things up vertical surfaces. And he needed to show that one of his models had normal residuals. And so he did a statistical model and had to show that his data differed from the model in a particular way, that if it was normally distributed, then it was actually a good fit to the model. And in order for him to show normality, there are a bunch of tests or whatever, but those tests weren't necessarily working with his data because of how they were. So he just included a QQ plot in his argument. So in the paper, he has a QQ plot that looks just like this, and his data fall right on a line. And then they have a couple of little outliers here at the end, but they're just kind of outliers. Most of it is right on the line. So the rule here is if you can fit a fat pencil on top of this line and it covers all your data, then that's a kind of a good qualitative evidence that your hypothesis, your hypothetical distribution is a correct one. All right, so there are questions about this plot. All right, so as another example, I could have taken the data. I'm checking online if there's any questions. Okay, so I could have taken the data drawn from an exponential, and then I might have looked at the exponential, and I probably wouldn't have guessed it's a normal, because you can think about data that's from an exponential, doesn't look normal at all. But let's just say I did say, I'm going to see, maybe this comes from the normal family. And so I'm going to take the data that came from an exponential. So notice down here, the range of that exponential, no lower than 0, and it goes to positive infinity. And then here, I've got my standard normal range here. So kind of centered on 0, but then going up to positive infinity and negative infinity. And when I compare this exponentially distributed data to the guess of a normal family, the QQ plot shows that it's bent in this way. It rises quickly and then it kind of falls off. So sort of curves down. This is a fat pencil, if you laid it on top of this line, would not cover many of the points. So this is a bad fit. There's not evidence that these data are normally distributed. And so there are general rules for these QQ plots. And so these are kind of general patterns that you often see. So all but a few points fall on a line. That's okay, there's just outliers. And then there's these points where you've got the left end is below, the right end is above, or the left end is above, the right end is below. And it gives you some hints about the tails of your data relative to your hypothesis. And then similarly, curved with increasing to the left. If I go back here, this is a curved pattern where there's a decreasing slope. So curved pattern with slope decreasing from left to right, data is relatively skewed to the right, more extreme values on the right. And that makes sense to me. So this is telling me that your hypothesis was a symmetric distribution, a normal distribution. But because I saw a curved pattern with slope decreasing to the right, the actual data has got much more skew to the right. It's had a lot more data points that are on the than your hypothesis. So your hypothesis was symmetric. This was a very skewed distribution, and it was skewed to the right. So in principle, you can look at these patterns and they can guide your choice of the next family. So you can say, if I fail the fat pencil test, I can use this kind of little decision hierarchy here, tree here, I guess just rule set here, to say, well, if not normal, then what? Well, then I can say, well, I need something that has more skew in it. So what are skewed distributions that I could pick? And oh, the exponential, that's a skewed distribution. So you could start looking at the skewed distributions, because clearly, based on this, because I compared it to a symmetric distribution, it's saying that it has a lot more skew than a symmetric distribution. So I need a skewed distribution. So the QQ plots help you find the coarse-grained families that, that your data might fit. So once you do the QQ plots, that's a good first step, but you want to round it off with one more thing. So the QQ plot tends to amplify the differences in the tails of the distribution. So you've got your hypothetical distribution, your actual distribution, and the QQ plot really focuses on how well they work kind of along the edges. And so that amplifies the difference of those tails. Once you've kind of fixed that out, then the PP plot helps you sort of focus on, well, what about the middle of the distribution? How well do they match there? And so we just sort of, it amplifies any differences there. So it's our last kind of check to see if we made a good family choice before we start worrying about parameters. And how do you do a PP plot? Sort the data exactly the same as the QQ plot, but then now we actually plot the sort of the CDF instead of the data points. And so we plot the rank. So I just did a little correction factor here, I minus 0.5 divided by n. We plot the rank against the hypothetical CDF for that data point. And so the data point goes into my hypothetical CDF, that spits out a probability, and I plot that against the rank of that data point. And that gives me my PP plot. So very similar to the QQ plot, I'm just plotting things instead of using the inverse. You know, it's kind of like this is like the other side, the complement to the QQ plot. And so as a motivating example here, so here's a histogram. This is data, these are data that I drew from a gamma distribution with these two parameters, 10 and 5. So that's the blue one here. The red solid line is that gamma distribution. The green hashed line is a normal distribution with a mean of 50 and a standard deviation of 15.8. And what you can see here is just visually, like if I didn't know that the blue histogram, if I didn't know that that was a gamma, it would be very difficult for me to tell the difference between these two hypothetical models for this. So I would then maybe go to the QQ plot. Here's the QQ plot for the gamma hypothesis as well as the normal hypothesis. So the gamma hypothesis are the red dots. The normal hypothesis are the green X's. And so for this one here, the QQ plot really doesn't show that one is that much better than the other. So the QQ plot says they're both kind of in the ballpark, but I can't really decide which one's better. So then I go to the PP plot. And with the PP plot, I can see that the red dots for the gamma distribution kind of fall straight on the line, whereas I get a lot more of a gap in these green X's. And so the green one, the normal, is a worse fit than the red one. And so I am going to conclude that the gamma is probably a better family for me to choose for these data. So that's kind of the process there. The QQ plot sees you, are you in the ballpark? And then you tune with the PP plot. You can't start with the PP plot first, because if your distributions are way off, the PP plot is not informative whatsoever. So you really have to be close already for the PP plot to make any sense. And so that's why you start with the QQ plot. So QQ plot, if your distributions are way off, then they'll be way off in the QQ plot, and you'll be able to interpret that, bring it back in, and then once you've got a bunch of candidates, then you can discriminate among those candidates with the PP plot. So, so basically QQ plots look for large linear relationships. Systematic deviations can help you guide your choice of an alternative distribution. Then you check for QQ plot deviations in the PP plot. So if your QQ plot looks pretty good, but you're not quite sure, there's a little bit of hairiness at the edge, at that point, it's a good idea to check the PP plot. And if the PP plot also shows you everything falls right in the line, then you're pretty much okay. And so the PP plot is a good way to discriminate among things that are similar in the QQ plot, or give you a little extra confidence if there's just a little bit of hairiness in the QQ plot. And so, and then, yeah, I was saying before, you don't ever start with the PP plot because the PP plots really kind of need things to be pretty close even for you to kind of get started with them. So those are things that I'm not requiring you to do on your input modeling report or Lab 8, but it's a nice thing to practice because these are tools that are very easy to use that you'll see as you start, going off and doing your jobs and things like that. Like people know what QQ plots are. and PP plots. QQ plots more than PP. QQ are much more used than PP. And they know the fat pencil test. And so you should know about these tools as well. All right, so any questions about these two plots, the PP plot and the QQ plot? The basic idea here, and including questions online. Okay. All right, great. So where we've gone so far is we've done the histogram, we've done the plots. And so now today, we are finally getting more quantitative, where let's start putting some parameters on the distributions, and then let's start testing goodness of fit, just like you do in the first question of homework G3. So let's do an attendance response, just to mix it up. So I'll put the link in the chat as well. And the question here is, which probability plot do you do first? A QQ plot or a PP plot? So I mentioned that one of them is useless if you do it first. So you do the one of them first, and then you can fine tune with the other one. Okay. All right. So some other questions, not attendance questions. So before we can start getting quantitative, we need to make sure we're on the same page about some of the metrics we're going to use. So what is the meaning of the level of significance, alpha? So if you go back to 385 or something like that, does anybody have a good definition of what alpha is, or level of significance is? And online, I'm also happy to look for responses there. Anybody? Yeah. So it's the probability of rejecting a null hypothesis if the null hypothesis is true. Is that correct? That's a beautiful answer. That's great. That's yeah. So that's what we mean by kind of level of significance is for a given test, it is the so-called type 1 error. So it is how often is a null hypothesis that is true going to get incorrectly rejected as a possibility. So that's what we say for a significance level. So okay, so that's a great, that's a definition you can memorize, but do you feel it? Do you really feel that definition? And that's what these two questions are about. So if I gave you a statistical test that had an alpha equal to 0, what would, how would they behave? So what do we know about a statistical test that has an alpha equal to 0, a type 1 error equal to 0? What's a statement about that test? How could you could develop such a test right here. You could name it after yourself or whatever, and it would be really simple to implement. It wouldn't be like a t-test or anything like that. It would be super easy for you to just, yeah. It's never wrong. That's right. What do you mean by it's never wrong? So how do you guarantee a hypothesis test? When you say fail, can you be more specific? Okay. What do we, yeah. And what would that outcome be? Well, what I'm saying, well, when you say an outcome, that sounds like, reject or not reject. Those are outcomes of hypothesis tests. So which would be the outcome? Everything would be not rejected. Yes, that's right. So this one up here, alpha equal to 0, I just design a hypothesis test where everything is not rejected. So somebody asks you, is this weird behavior? And as long as you said no, then your alpha is guaranteed to equal to 0. So we have null behavior. So null behavior is like, like, oh, Ted's wearing a navy blue shirt. And you could say, is this novel for me to wear a navy blue shirt? And you could say, well, what's the null hypothesis or whatever. And so we can look back at historical data or whatever. If you just said that, no, it's not weird, then you're never going to make a type 1 error. You might make a type 2 error, but you won't make a type 1 error. So the type 1 error is assuming the null hypothesis is true, you incorrectly reject it. So assuming everything is normal, you incorrectly say things are weird. So this is the conservative thing where you're saying, I don't detect any weirdness. I'm just going to assume everything's normal all the time. And that way you never commit type 1 error. So then the flip side of that, what happens when you have a hypothesis test where alpha is equal to 1? This is sort of an easier question now that we've answered this one. What would such a hypothesis test look like? You could build a very simple engine that would have an alpha equal to 1 guaranteed. Everything's rejected, right? And so you immediately bias to say everything's weird. Like, you know, so that's what people ask you. Is it weird? That's a hypothesis test. Are things different from the null hypothesis? Or the null hypothesis is whatever the nominal behavior is. And if you always say things are weird, if you always say things are rejected, it is not normal, then you're guaranteed to have a type 1 error rate of 100%. That means that when the null hypothesis is true, you're guaranteed to reject it. Now, you will sometimes still correctly observe that things are different from the null hypothesis, but these error rates are in the condition when the null hypothesis is true. That's how we're measuring them. So that's kind of what I want you to sort of focus on here with type 1 error is under the condition where the null is true, how often do we incorrectly detect a difference from the null? Here, you never detect a difference from the null because you just never detect a difference from the null. You just say, without even looking at the data, no difference. Here, you always detect a difference from the null. So without even looking at the data, you say difference all the time. And that's where you get that. So a real hypothesis test lives in the middle. And we have to design them so that they have an error rate as desired. But the right error rate sometimes actually depends on your application, because sometimes you care more about false positives than you do about false negatives. And that's what we'll kind of get into here. But thinking that way through, let's operationalize this a little bit more. Think about the chi-squared test. As the chi-squared test is used on distributions that are farther from their null, what happens to the chi-squared value? Does it go up or does it go down? So my null hypothesis is, say, uniform distribution, and I give you data that is not very uniform, and then I give you data that's even more not very uniform. Did the chi-squared statistic go up or down as I got farther from the null? Anybody? Any thoughts? Remember, I said you can conceptualize the chi-squared statistic as a type of metric relative to the null. So I've got my null is a uniform. I put in data that's kind of uniform, I get a chi-squared statistic out. I put in data that's really not uniform, I get another chi-squared statistic out. Did that statistic go up or did it go down? As I got farther from the null. How many people say up? And then online, you feel free to vote as well. How many people say down? Okay, all right. So what if I told you that the chi-squared statistic can be viewed as a difference from the null? So so if you think about it, in all those little bubbles where you're taking how many expected how many expected in the bin minus how many observed in the bin, each one of those are like a difference from what was expected for this bin, and we're adding all those differences up. So really the chi-squared statistic is a difference from the null. If I say that, then how many people say as you get farther from the null, the chi-squared statistic goes up? So how many people would vote for up now? How many people would vote for down? All right, so up was the answer that I'm looking for here. So chi-squared statistics and KS statistics, the statistic itself, the thing you calculate, is meant to be a, qualitatively speaking, a difference from the null. So the farther you get from the null, the bigger the statistic goes. So now think about those critical values. I want you to be linking in your head critical values and alpha values. So if I make my alpha value very small, so on this previous slide, that's this one here, if alpha is close to 0, so it's very, very small. So remember, we said when alpha is close to 0, we almost never reject things because we don't want to make any errors. So if I make my alpha value very small, what happens to the critical value for a chi-squared test? Does it get very large or very small as well? Any guesses? So I see a couple sort of motions, like maybe it goes down. Does anybody else have any thoughts? So remember, the chi-squared statistic, the farther you get from the null, the larger the number is. And so the critical value, that is the value at which you say, that's too big. I'm detecting a difference from the null. So if alpha gets small, and I go to my table in the back of the book to look at the chi-squared critical value, does the critical value go up? Does that boundary get higher, or does it get lower? Anyone brave? Have a reasoning here? I see it up here, so I saw kind of a down in the class and an up in the chat. Nobody. It's October, it's very scary. What I'm trying to get at here is that this boundary, as the chi-squared value, or sorry, as the alpha value gets low, the chi-squared boundary gets high. Because think about that, when alpha is equal to 0, you don't reject anything. The only way you never reject anything in the chi-squared test is if the critical value is infinity. Because the only time you reject things is when the chi-squared value is bigger than the critical value. So as the alpha gets small, the critical chi-squared gets high, and vice versa. As alpha gets closer to 1, you reject everything. Well, the only way you reject everything with a chi-squared test is if the critical value plummets to 0. So, you don't even have to look in the back of the book if the critical value is equal to 0. You can say, well, if my alpha is equal to 1, I don't have to do the chi-squared test because I know any chi-squared value I get is going to be greater than 0. So I can just immediately say reject. So when you look in the back of the book at those values, notice those patterns. As you walk from column to column, as you go to different alpha values, look at how those critical values are changing. As the alpha values are getting large, the critical values will be getting smaller, and vice versa. And so that's what I need you to sort of starting to feel that intuition about these things. Okay. All right, so any questions about that, about this idea of the relationship between critical values and alpha? We're talking a lot more about alpha as we go on in the next couple of lectures, and beta. All right, and so then other questions I could ask you, like the meaning of a p-value, and so we kind of already kind of beat this over the head, but whereas the alpha is a limit on your error, the p-value is actually the probability that in the condition that your null hypothesis is true, what is the probability that I would see a statistic that is this large as my data produced or larger? And so that is what the p-value here is. So I calculate my chi-squared statistic, it comes out to be 11.7. And then the p-value is to say, well, under a null hypothesis, I would get different chi-squared statistics out. So when my data are uniform, if I were to draw 100 data points, I would get a certain chi-squared statistic. And then if I drew another 100, I'd get another chi-squared statistic. And that would come up with a distribution. And then that distribution sometimes would produce large values, but most of the time would produce small values. And so then the question would be, how often do I get a value that I got or larger? And that's what a p-value is, right? So it's the probability that the deviation you observe from the data, the deviation from the null you observe from the data, is at least as large would be at least as large given that you're under the null. So that's what your p-value is. So we often use the p-values with the alpha as an alternative way for us to sort of have a critical level here. So we say that, well, if my p-value is less than alpha, then I'm guaranteed to have a type 1 error rate of no higher than alpha. So that's the idea here of comparing the p-value to alpha. So I can either compare the statistic to the critical value, or I can compare the p-value to alpha. Now, what I want you to be thinking, so any questions about that? What I mean by the p-value here, where it's this idea, and I'm gonna draw, in the next couple of lectures, I'll have diagrams that'll make this even clearer, but this basic idea that it's the probability I will get a deviation from the null at least as big as the deviation I see in these data, given that my null is true, the p-value. All right, now, the thing that I want you to start thinking about that you don't think about when we first start teaching these things is what are all of the different reasons why you can get low p-values? And what are all of the different reasons why you can get high p-values? And to motivate that, let me do a little hypothetical, so to speak, here. Let's imagine you flipped a coin. It's like out of my pocket, if anybody still has coins, you flip a coin twice, it comes up heads twice in a row. Now I have two hypotheses for the fairness of that coin. It could be a fair coin, equal probability it comes up heads or tails, or it could be a biased coin that always comes up heads. The p-value under a binomial test for a fair coin is 50%. So under the null hypothesis, it comes up heads 50% of the time, it comes up tails 50% of the time. So if I get a head, then the binomial test value is 50%. Now, the biased coin that only comes up heads has a p-value of 1. So if I just judge hypotheses by p-values, then every time I flip a coin twice and it comes up heads both times, I have to conclude it must be a biased coin. Okay, but that just doesn't seem right. What's the problem with this, with concluding that it must be biased because it came up heads twice? Yeah, not enough data. That's right. That I flipped it twice, and it's very likely actually that it's going to come up heads twice. Now, it's even more likely that it'll come up heads twice if it was a biased coin, but it is very likely that it's going to come up heads twice if it's a fair coin. So it's not really a fair test for me to then say, because I didn't take enough data. So that's the one thing here, that high p-values often mean low data. So if you see a high p-value, you cannot conclude acceptance unless you have something called statistical power, which is what we're starting to learn about in this lecture and even more so in the next lecture. So we have another thing, beta. So that's when we need tests that have a high statistical power, and that lets us accept things. But we cannot accept hypotheses for this example right here, because most of the time you get high p-values, it's because you have low data. Now, to sort of flip that on its head, so to speak, imagine I flip a coin 200 times, it comes up heads 90 times. All right, well, so under the null hypothesis of a fair coin, the p-value I get is 17%. And I say, all right, 17%, that is higher than my alpha, do not reject. Do not reject the fair coin hypothesis. But imagine I flipped the coin 2,000 times and it came up heads 900 times. Well, now the hypothesis of a fair coin, wait for it, has a p-value that is vanishingly small. Same really statistics here, same proportion came up heads, but now I have an extremely small p-value. And so I might say reject the fair coin. Now, the question is, what happened here? So, so you could argue that 900 out of 2,000 is not a fair coin. It should be 1,000 out of 2,000 if it was truly a fair coin. But you could also argue that practically 900 out of 2,000 is fair. So based on this, whatever I'm describing as fairness, then it sort of affects this hypothesis here. I need to come up, my hypothesis is that knife edge of exact fairness, where 1,000 out of 2,000. And once I take enough data, I will be able to detect a difference from this level of fairness. This is an ideal here. As another sort of example there, I might have brought this example up before, Pluto. the gravitational effect of Pluto on me may be having an effect on my mood. But in another model of the world, another hypothesis about my mood, Pluto's not involved. Now, if you took enough data on me, my guess is that you would eventually detect the influence of Pluto on my mood. But it would be such a small effect that it would be practically insignificant. And that's the same thing kind of coming up here. If you take enough data, you will eventually detect a difference from your ideal hypothesis. And unless your ideal hypothesis is spot on, then you were going to probably incorrectly reject this hypothesis. So extremely low p-values coupled with extremely high sample sizes should not be trusted. So if you see a low p-value and an extremely high sample size, now extremely high is going to depend on your application, then you should go and really ask somebody, well, what's the effect size? In other words, was it fair to call a fair coin a 50% coming up heads or tails? What if we said really anything between 40% and 60%, that's a fair coin? Under that, I might get a very different answer. Does that make sense to me? So low p-values are, high p-values should not be trusted when you have low sample sizes. Low p-values should not be trusted when you have high sample sizes. Okay, does that make sense? Any questions about that? Also checking the chat. All right, it's nuanced, but we're going to see more and more of this as we go on. And what I'm trying to motivate here is we're going to find that point estimates, we're going to gradually transition away from, so that by the end of the semester, we're only going to use interval estimates. And I am going to motivate to the use of things that better incorporate so-called effect sizes. So we do that kind of crudely in this class to get us on the ball there. But if you take any other more sophisticated statistics classes later in your careers, then you'll start going into generalized linear mixed modeling, where you formally account for effect sizes, where it's not purely about rejecting an ideal hypothesis. Yeah. Why would more samples lead to rejection? Because with the more data, you have more ability to detect a difference from an ideal. And so what I guess I'm saying is here is in 2,000 coin flips, if it's truly a fair coin, it's actually pretty unlikely that it's going to come up 900 times heads. It's probably going to come up, somewhere between 950 and 1,050 or something like that. So this is sort of an outlier in the null hypothesis of fairness when I flip the coin 2,000 times. And that's a so-called power analysis, and that's what we start to do in homework G3, is exactly that question. So in G3, basically what the second part does is your boss tells you, this is my acceptable effect size. In other words, fairness is an ideal, but imagine your boss said to me, I don't need you to detect fairness. I need to detect anything outside of 5% of fairness. So you could say anything from 45% fair to 55% fair, that we're going to call that fair. And like 45% bias, 55% bias, we're okay with that because we can't make a totally unbiased coin. But as long as it's within 45%, 55%, we're okay with that. Once I give you that bound, there is a formal way called a power analysis where then I can say, based on the variance in the coin and the bound you've given me, then we need to take this many samples to detect whether you are outside that range or inside that range. And so that is the so-called power analysis, which is super important to do, and which we haven't talked about so far, which is why we get into this stupid conundrum here, where as I just take more and more data, I am guaranteed to eventually reject every hypothesis, because you're never going to be dead on the hypothesis. And so there will be a difference, and with enough data, you'll detect the difference. Okay. All right. So this is just summarizing that. Large p-values only meaningful if there is enough data. And what we mean by enough, that comes out of the power analysis as well, which is what you'll start doing in the second part of the homework. And you can always generate lower p-values by taking more data. And this is why big data people, like in machine learning and data science, rarely use things like t-tests, or if they do, they use them in a very specialized way, because things like t-tests are designed to detect differences with low sample sizes. But once you throw a lot of data at them, your t-tests always come out rejecting your hypotheses because they're too sensitive. And they're so sensitive because they've been designed for low sample sizes that when you throw a lot of data at them, then any small deviation from that idealized hypothesis will be detected. And you'll conclude that that hypothesis should be rejected, when practically you're close enough to that hypothesis, you shouldn't reject it. And that's what the power analysis is all about, which again is what we start on in this homework. So, and this is what I'm just kind of saying as we move forward. In this class, we're going to motivate the interval estimates and try to kind of get into what we mean by effect sizes. And then in future classes, if you're interested in statistics and inference and all that, then you'll find out that there's a whole slew of tools from generalized linear modeling that that make this give you a whole lot more power to do these sorts of things without getting into these sort of puzzles. And I might skip over this, but just for time. But usually at this point, you know, baseball's going on, and at this point in the class. And so I like to point out that best of 7 series in sports tournaments have this peculiarity, statistically speaking, in that they don't actually end up determining who's the better team because they don't play enough games. And so the basic gist that I'm kind of getting here is if you sample, and so what's the null hypothesis in, you know, if 2 baseball teams play each other, the null is that they're equally matched. And so you want to detect the difference from the null. You want to detect that one team's better than the other. And so you want to say, well, how many games do they need to play in order for me to detect that one is better than another? And then based on the outcome of those games, when can I conclude that I've rejected my null, that they're equally matched? And if you look at, say, a 7-game streak where there's 6 wins and 1 loss, it turns out a binomial test gives you a p-value of 12.5%, well above 5%. And so in order for you to actually reach a significance level of 5%, you need to play 7 games and have them all be wins. And then you get to a 1.5%. But you never would play 7 wins, because once you won the first 4, then you'd stop the series. So then you'd say, well, what happens when you just do 4 games where they all 4 be 4 wins? Well, that p-value comes up to the 12.5% again. So it's really no better. So then you say, all right, what if, and you might even call this boring. But as you get 5 games with 4 wins, so the other team starts to win 1, then you're at 31%. So you're even farther from your 5%. And when you finally get to 7 games with 4 wins, so it's a 4-3 split, then in that case, this is the most exciting series to watch, but you're at 54% for this binomial test p-value. So you're way above 5%. And this is now like fair coin toss territory. So what's beautiful is that they figured out a way to keep people watching for 7 whole days, you know, all the commercials and whatever, when in the end, the outcome with respect to detecting which team is better is no better than a coin toss. So if you really wanted to, if you really cared about which team was better, to get rid of the randomness and, you know, deterministically find to get to the point where you could say this team is better, we would need to actually play far more games. But no one would want to watch more than 7 baseball games. You know, I mean, so I'm not trying to be too flip here, but, you know, you could say people stop caring after a certain number of games. And so, you know, to play enough games to determine which team is better would end up not being a good marketable way to market, you know, TV sports. So we're stuck with 7 games because people don't want to watch more than 7 games. But 7 games is this interesting feature that in 7 games, you can't actually determine which team is better. So in the end, you get really excited because your team won. You might get really sad that your team lost. But in a 7-game series, doesn't really mean anything based on who wins or who's lost if we at least think statistically. So we would never design an experiment like a sports tournament. It just goes to show that sports tournaments aren't about detecting who's better. They're just about entertaining. So, how this links to the homework is that we're saying that 7 games does not have a so-called enough statistical power to detect the difference from the null. And so it's basically flipping your coin twice and it coming up heads. All right, so, and then if you really, want to take that even farther, you could think about voting as well. So really close elections that come out to a 49%, 51%, outcome, and you say, there's a winner. Well, statistically speaking, there's not. You probably don't have enough samples to detect the difference from the null when your outcome is that way. And you probably need to go to a recall election or something like that. And eventually you'll get enough data so places that have recall elections or ranked choice voting and all of that sort of stuff, that is an attempt to get statistical power in the most economical way. But in a one-off vote, you're kind of, you might get lucky and it'll be like 10 to 90. So 10% to 90%, in which case, you probably did detect the difference and you really can detect what the population wants. But if it's 49 to 51% with how many people vote in say this country, then you really have no idea who won. So just things to think about statistically about these, whether these are good experiments that are designed here. All right, so of all of that, type 1 error rate and statistical power, these are things I'm not going to mull over too much here because we're going to talk a lot about these in the next couple of lectures. So with that, any questions about this basic overview? We're starting to get into this. We want to be talking about alpha, beta, and statistical power very conversationally by the end of the semester. So this is our foray into that, first foray into that. And we'll talk about beta more next time. Okay, all right, so maybe we'll do a quick second attendance exercise. And the question here, I'll say, is if a statistical test always rejects a null hypothesis, regardless of data, does it have a high alpha or a low alpha? Okay. All right. So so we just talked about QQ plots and PP plots. I said we're going to start talking about choosing parameters and doing goodness of fit stuff. So probably have to carry on a little bit of this next time. So hopefully we're clear what I mean by parameters. Each one of these distributions has a certain set of degrees of freedom that can still be set on it. So in a binomial distribution, we've got parameters n and p. So n trials that each have a success probability of p. And so those are 2 parameters we put into the distribution that give it its shape. And so sometimes they have physical meaning, the number of trials, the probability per trial. Other times they're just shape parameters. And so the range of a uniform distribution, it just defines its range. Like for a beta distribution, which we haven't really talked about, the parameters there have 0 physical meaning. They really, well, you could argue they have some meaning, but it's very mathematical. And so whereas that's very different than the uniform distribution where you can say, well, A, it's no lower than A and it's no bigger than B, but these all sort of affect the shape of the distribution. And so the common shape parameters that we'll talk about is the so-called location parameter. So this is like a generalized version of mean. So a location parameter is and if you have a probability distribution that has a location parameter, what someone is telling you is if you took a member of that family and you added or subtracted from the location parameter, so you swapped the location parameter, made it something else, you would then still get a member of that family. So the normal distribution has a location parameter because a normal distribution could be centered at 0 or it could be centered at 5, and it's still a normal distribution. Similarly, there are these so-called scale parameters, and a scale parameter is a parameter that if you were to stretch or shrink it, so multiply it or divide it by something, the resulting distribution would still be in the family. So a normal distribution as a scale parameter, because if you took the standard deviation and multiplied it by 5, then you would get a different normal distribution, but it would still be described as a normal. So it would still fit the formula of a normal distribution. And so we actually refer to the normal distribution as one of the few distributions that are so-called location scale. And so there's a wide variety of distributions, but not maybe so wide, that have both a location and a scale parameter, and we call them location scale distributions. And so sometimes when we do input modeling, we'll say we just need a location scale distribution here, and we'll say that, and we'll just put the normal distribution in because that's the easiest one, but this generalizes to any location scale distribution. So those are things that we say by that. An exponential, for example, it has a scale parameter but no location parameter. So the exponential scale parameter is 1 divided by its rate parameter. And so we'll use the term rate to mean 1 over scale. So if I say I have a parameter that is a rate, I'm implicitly telling you that it is a scale parameter, but the magnitude is 1 divided by it. So these are terms that we sometimes use: location, scale, and rate. And everything else we just refer to as shape parameters. So those are just some terminology. Now, I don't want you to get the parameters confused with the summary statistics. So, and I won't dwell on this because you guys have gotten this in a bunch of your other classes, but if I give you data, before we model it, you can take the mean of that data. That is not a parameter, that is a summary statistic of the data. So I'm taking all that data and I'm estimating the mean of that data without asserting that there's any model that came from that. The variance, or the square of the standard deviation, is similar to that. So you guys have learned these formulas. I just want to remind you that when you calculate variance, it is super important to divide by n minus 1, not n. So the sum up here will be a sum that has n terms in it. And so you think variance, it's kind of taking an average. It's like an average variation. That's what variance is. So you should divide by n because there's n terms here. But there's only n minus 1 degrees of freedom up here, because if you use the sample mean in your variance calculation, then if you know the sample mean, you only need to know n minus 1 other data points, and the other data point is fixed because you had to calculate the mean somehow. So if you're using the sample mean in your variance calculation, you only have effectively n minus 1 data points that you're summing over. And so that's why you have to divide this by n minus 1. And that should maybe make sense to you if you think about if I only had 1 data point, so I could calculate my sample mean from it, it will be exactly equal to that data point. If I divided if I try to calculate variance by dividing by n, then if n is equal to 1, I'm going to get a finite value of my variance. But in reality, if I only have 1 data point, I don't know anything about variance. So really, I need to divide by 0, because really it's like the variance is kind of infinite if I only have 1 data point. So dividing by n creates a so-called biased estimator of variance. And so whenever you calculate variance, make sure you divide by n minus 1, or else you will bias your estimator. It'll look like it has lower variance than the data actually do. And we can do these games with discrete random variables as well. Again, you've probably seen all of this before, so I don't want to dwell too much on it. But if I give you a distribution where I say I have these k outcomes, so outcome x1 through xk, and they have these k frequencies. So outcome x1 occurred this often, outcome xk occurred this often. Then to calculate the mean, I multiply the frequencies by the outcomes and then sum all those up and divide by n. And to calculate the variance, it's kind of similar to that, where I can subtract the outcome from the mean, the sample mean, and then multiply by the frequency, and then again divide by n minus 1. And if I don't give you a discrete random variable, but I alternatively give you a continuous random variable, but I give you a histogram, you kind of treat it like a discrete random variable, where you take the median of each one of those bins and treat it like a discrete outcome. And then you've got a frequency for each median, and then you do that same formula again. So those are 2 important summary statistics: sample mean and sample variance. They aren't parameters, but they often will pop up in choosing the best parameters, because often the best parameters will have these in the formulas. So any questions on this? Hopefully all this is review, the sample mean, sample variance, and the n-1 stuff. Okay. Something online. All right. So as an example, I give you a Poisson distribution here. So I've got the outcomes, 0 through 11. I've got how often they were observed, the frequency data here. And so from there, I can calculate the sample mean by multiplying each. I basically multiply across here. So I get a 0 for this row, a 10 for this row, a 38 for this row, and so on. So I multiply across, add all those up together, divide by n, and I get a mean of 3.64, which is roughly here or so, which if you think about your statics, that's about where this shape would balance itself. If it was in static equilibrium, you can put a little fulcrum under it there. And then I can then calculate the variance using the formulas from the previous page. There's a little trick where I can just take I can estimate the squared, like the second moment, and I can subtract off the square of the first moment. So that's I think a trick that I'm using here. But either way, you can just use this formula here, and you'll end up getting a sample variance of 7.63. Now, this is partly an example, just to give you some numbers for you to try this to make sure you know how to do the formulas here. But the key thing that I want to point out here is that for a Poisson distribution, the distribution actually has the mean equal to the variance. That's one of the interesting things about a Poisson distribution. It's a discrete distribution, has one parameter, and that parameter equals both the mean and the variance. But for these data, the mean and the variance do not agree. In fact, they're very far off. So this is an example of why point estimates are really, really dangerous to interpret, because this is an estimate of the mean, 3.64. The real mean is actually within a confidence interval that is centered around the point estimate. And that's what we're going to move toward, is using confidence intervals. Similarly, the real variance is in a confidence interval. And I can guarantee you that the confidence interval of the variance overlaps with the confidence interval of the mean, and because they came from the Poisson. But if I just look at the point estimates themselves, then these numbers might differ. And so if I want to say, well, what's the best alpha to use when I'm modeling these data, I now am not sure what to use. Should I use the 3.64 or the 7.63? Because in theory, the variance should be equal to alpha, but so should the mean. So we need a way, other than just blindly choosing a sample statistic, to fix, a good way to fix whatever the variables should be here. And that's what we're going to talk about here. So for all of these sorts of things, it's a similar story. The summary statistics describe the data without a reference to a distribution. How do we find a rigorous way to come up with good point estimates of the statistics themselves? And where I'll kind of close on here is this maximum likelihood method. And so for a discrete, which again, this should all be reviewed too, but for a discrete random variable, I've got a probability mass function. For a continuous random variable, I've got a probability density function. Now, we've got the parameters, which I've got as theta for those distributions, but I've also got the data that I've sampled. And so normally we think about, I've got parameters, and then I can say, what's the probability I get these data? But when I cast these as so-called likelihood functions, it's the reverse. So a likelihood function takes the same function that we use for probability mass or density, but I put the data that I sampled in and treat it kind of like a parameter. And then I kind of ask, what's the sort of probability that these parameters could have produced these data? And then I can maximize that likelihood to pick the best parameters. So to give an example of that, here's an exponential. I know the probability density function for an exponential. This is just for a single exponential. So let's say I drew, I don't know, 20 data points or K data points that are in data points that I'm claiming are from an exponential. And I'm going to choose the best rate parameter for that exponential. So in theory, I would need a compound probability or a joint probability distribution for all n of those points. But if I assume they were drawn independently, then the joint distribution is just a product of all the individual distributions. And so I know the formula for all these individual distributions. It's that right up there. So this joint distribution becomes this right here. So this is just taken by multiplying these together and combining all the arguments. And so what I've now got here in this joint distribution is a rate parameter that I would like to pick, and my data show up as if they're parameters of this distribution. In reality, the rate parameter is the parameter, and these data are things we normally think about what's the probability of. But for likelihood, we flip it around, we plug in the data as the fixed things, and then we try to pick the parameters here. So I'm going to do, take my data that I've taken out of the real world, plug it in here, and do a little calculus. I take the partial derivative of that probability density function with respect to the parameter. I get this. I set that thing equal to 0 to solve for the optimal rate parameter, and I get this formula right here. And so this is telling me that the maximum likelihood guess for the rate parameter of an exponential just happens to be, and this is pure coincidence, 1 over the sample mean. So if I take the mean of my data, my inter-arrival times, I'm going to say, my inter-arrival times I think are exponentially distributed. What's the best rate parameter? I take the mean inter-arrival time, so whatever, 5 minutes or whatever, and then 1 divided by 5 minutes, that gives me my optimal rate. So that is the maximum likelihood estimate for an exponential rate parameter there. And it just happens, again, be in terms of the sample statistics. It doesn't have to be that way, but very often the sample statistics crop up in these formulas, which are one of the reasons why the summary statistics become useful quantities. Now you can go online or in your book, and for a bunch of different distributions, you can look, what is the maximum likelihood estimator for their parameters? And so for a Poisson, if I look up in the book or online, what's the maximum likelihood estimator for its parameter alpha? It just happens to be the sample mean. So this answers our question from earlier. I could get the sample variance or the sample mean from the summary statistics. And in theory, either one of them should match alpha. But it turns out the maximum likelihood estimate is the sample mean, not the sample variance. Exponential, already covered that. Normal distribution, it's pretty easy. The best parameter is the sample mean for the mean. The best parameter for the variance is the sample variance, so long as you use the n-1 form. And then there's a bunch others that you could look up. So I'm not going to go over all of these formulas, but I want you to know that maximum likelihood estimation, MLE, this is a common way for you to come up with a good parameter if you're confident about the family. And you can just Google for these things. What is the MLE for the parameters of a gamma distribution? And you go up and you look it up, and it gives you a formula that will take your data in and spit a parameter out, and then you're done. So that's one way we can get these point estimates. So any questions about the maximum likelihood method here? I'm not going to ask you to do any calculus for this stuff. I just did that little derivation just so you could see that there really is math underlying all of these things. Okay. All right, so that's good. So the only thing we've left off now is the modifications of the chi-squared and the Kolmogorov-Smirnov, which are very minor. They're very easy to cover, so we will cover those next time. And you've already done the chi-squared, I think, probably in 380, if not some other courses as well. So we'll cover that next time. But so I'll stop here. So we'll have our closing attendance question. And the question here, I'll say, is when you are calculating the unbiased sample variance and you are using the sample mean in the formula, what do you divide by in the denominator? So basically I'm asking for what's the denominator in the unbiased estimator for sample variance. Otherwise, that's all I've got for you. So have a good weekend, and I will see you Tuesday. I'll hang around for any questions. And online, I am going to stop the recording, but I'll leave this online for anybody who has anything. Otherwise, I'll see you next week.